we'll talk about multi-phase pore fluids. I said in the last few minutes, I said, hey, I'm talking about a gas reservoir that's got SW of 0.2, because that's reality, right? We don't really have just pure gas in the pores in a hydrocarbon reservoir. So we're going to talk a little bit about that. And here's the statement. For any composite medium in which each component is subjected to the same change in isostatic pressure, the bulk modulus of the composite medium is given by the Royce average, also known as the suspension formula, sometimes called the Wood formula. In the case of just two components, you could write this way, but it's generalizable. It could be written as the sum of F sub I over K sub I sum, right? And so we had two components, let's say water and hydrocarbon. 1 over K sub F is equal to the water saturation, the water fraction over the water modulus plus the hydrocarbon saturation, or 1 minus SW over the hydrocarbon modulus. And the composite density, of course, just linear. So this is whatever, springs in parallel, not in series. And so that's the way that works. You can easily convince yourself of that if you just consider what happens to the separate components that are subjected to the same stress. Okay. What does that look like for our fluids? And here are our numbers, some reasonable numbers. You're going to see a lot more than reasonable numbers. These go for Z, for water depth of 6,000 feet and sediment depth below the sea bottom of 8,000 feet. For brine, reasonable number at 100 grams per liter salinity. Seawater is about 30. Saturation probably around about 200 grams per liter. Density is 1.06. The velocity is a little higher than our standard 5,000. You think of 5,000 feet per second or 4860 or something in shallow water. Seawater, but it's a little higher because the pressure is higher and the salinity is greater. And the bulk modulus for these two numbers turns out to be, in these units, 3.05, okay? For oil, 30-degree gravity oil, with a gas-oil ratio of 940 cubic feet per barrel. Don't you love that term, 9 cubic feet per barrel? I'm not sure whose bright idea that was, but anyhow, if it helps you, I mean, there's 5.6 cubic feet in a barrel. This density of such an oil. This is a reasonable estimate of the velocity, I will say, and this is the resultant bulk modulus. For the fluid, remember, bulk modulus is rho V P squared, right? So what do we got here? We got a ratio of 12 to 5, a little over 2 to 1. For gas, methane, because we're at great pressure, this is normally pressure, at 14,000 feet down, 14,000 foot water column, right? So we're under a lot of pressure, and the density is surprisingly significant. 1, 2, 3. And the velocity, nevertheless, is quite a bit less than the velocity of the fluid, and since the bulk modulus goes as the square of the velocity, the bulk modulus is still quite low. Very low. So now, I took the extreme case. I was showing you gas effects. I was showing you extreme effects. This is what's going to count. Let's look at what happens with this suspension formula when we put things together. So here's the density. This, by the way, this 940 cubic feet per barrel oil is about 50% of saturated oil. Oil which in the ground, at those reservoir conditions, would be saturated with dissolved gas. So, well, that's pretty easy. The density is linear, right? So what we're plotting here is as a function of the concentration, water concentration in this case. Over here I've got water, so it doesn't make any difference whether I got gas or oil because it's all water over here. And over there I've got pure oil. What's a water saturation of 0.2? It's over here. So for composite fluid density for a gas case in this particular setting would be about 0.4 grams per cubic centimeter, and for oil about double that for a commercial reservoir. Much less contrast if I was over here at low gas saturation. Okay, what about the bulk modulus? Well, for the oil case, it's monotonic. We were at 1.3 over here, we're at 3 or something over here, we're over 3 over here, and that's what it looks like. For gas, it is monotonic in this particular case, but brother, it stays low for most of the time. Now, for most of the range of water saturation. So I want you to think about that a little bit. That formula, the Royce formula, is, what's it going to do? If I have a glass of beer and I got bubbles in it and at atmospheric pressure, and I close that baby off and I start squeezing on it, it's going to be very hard to compress it. Not really, because what's going to compress right away? The bubbles. The water, which is it's the beer, is not very compressible, but the bubbles are easily compressed. So the volume change will, at first, look like the volume change that I would get if I had nothing but gas in there. That's what that parallel spring formula says, and that's what this is saying. And a consequence of that is, remember, Gossman cares about the case of F in that second term. A consequence of that is going to be you can't tell the difference between the reflection coefficient for this guy and the reflection coefficient for this guy. This is a commercial reservoir. This is not. This is not. This could be a blown trap and residual oil saturation, residual gas saturation, a few percent. No continuous hydrocarbon phase, no production, illusory, sometimes called fizz gas, low saturation gas, with a lot of names for this in the industry. We're going to see this in spades later, but this is what gives rise to this composite of fluid in the pores, multi-phase fluids. Well, gee, this is fluid, right? So composite fluid though it may be, we got the bulk modulus, we've got the density, we can calculate the velocity. Rho Vp squared is equal to K for a fluid, right? So we can calculate the velocity. Let's look what the velocity looks like. There it is. You believe this? The velocity at these intermediate concentrations, lots of them, is lower than the velocity at either endpoint. You know, when I was a freshman in college, they had a physics demonstration about once every 2 or 3 weeks. And the guy would always start it by setting up the equipment, telling you what experiment he was going to run, and then asking people to predict what the outcome was going to be. And let me tell you, what you learn very quickly is your intuition stinks until you've studied some equations. You don't know what's going to happen. You were rapidly understood that you didn't know anything. It was one of the most effective ways of teaching us. And I'll tell you, this is true. There's good evidence for this, even empirical evidence of it, in sea bottom sediments, where you have essentially a suspension, and people have made velocity measurements on the deck of cores taken from sea bottom sediments that have velocities go up to 70%, that is, fluid volume fractions of 70%, and they use a constant temperature bath of fluids so they know exactly what the end number velocity is of the brine. And the suspension formula fits the data very, very well, and over most of the range it's lower than either end number, which we know that for the solids is way above, and for the brine cases. I didn't show that here. It was done back in the 60s by a lady by the name of Charlie Schreiber. So yes, that does happen. The Royce average applies to any composite system in which all components are subject to the same stress, such as suspensions and immiscible fluid mixtures. It predicts that the composite bulk modulus is not linear in concentration, but since the density is, the propagation velocity of the mixture may be lower than that of either end number. Note, the oil is monotonic, this water be gas is not. The gas can be two in certain situations, depends on what pressure you have, et cetera, whether that flattens out. This means the velocity computed with Gaussman's equation for gas cases will not be sensitive to gas. This is the take home. Right? This is the take home. Rick asked about false positives. This is going to give you a false positive.